the second as the base unit of time in the International System of Units. It is qualitatively defined as the second division of the hour by 60, the first division by 60 being the minute. It is quantitatively defined in terms of a certain number of periods, about 9 billion, of a certain frequency of radiation from the cesium atom, a so-called atomic clock. Seconds may be measured using a mechanical, electric or atomic clock. In the year 1000 CE, the Persian Muslim scholar al-Biruni first used the term second in Arabic and defined it as 1/86,400th of a mean solar day. In the 13th century, scientists who wrote in Latin, including Bacon, and later Kepler and Tycho, used the Latin term parti minutae secundae to mean a unit of time which represented the second small part of an hour as the division of 1 minute by 60. The use of the word second in English began in the late 16th century. The definition remained unchanged from 1000 until 1960, at which time it was defined as the fraction 1/31,556, 925.9747 of the tropical year for 1900 January 0 at 12 hours ephemeris time. However, astronomical observations of the 19th and 20th centuries revealed that the mean solar day is slowly but measurably lengthening, and the length of a tropical year is not entirely predictable either. Thus, the Sun-Earth motion was not considered a suitable basis for the definition. With the advent of atomic clocks, it became feasible to define the second based on a fundamental property of nature. Thus, a mere 7 years later in 1967, the International Committee for Weights and Measures changed the definition to the duration of 700,992,631,730,192,631,770 cycles of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. In 1997, the CIPM added that the preceding definition refers to a cesium atom at rest at a temperature of 0 K. SI prefixes are combined with the word second to denote subdivisions of the second, e.g., the millisecond, the microsecond, and the nanosecond, though SI prefixes may also be used to form multiples of the second such as kilosecond. Such units are rarely used in practice. The more common larger non-SI units of time are not formed by powers of 10. Instead, the second is multiplied by 60 to form a minute, which is multiplied by 60 to form an hour, which is multiplied by 24 to form a day. The second is also the base unit of time in other systems of measurement. The centimeter gram second, meter kilogram second, meter ton second, and foot pound second systems of units. International second. Under the International System of Units, since 1967 the second has been defined as the duration of 700,996,317,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. In 1997 CIPM added that the periods would be defined for a cesium atom at rest, and approaching the theoretical temperature of absolute zero, and in 1999, it included corrections from ambient radiation. Absolute zero implies no movement, and therefore zero external radiation effects. The second thus defined is consistent with the ephemeris second, which was based on astronomical measurements. The realization of the standard second is described briefly in a special publication from the National Institute of Standards and Technology, and in detail by the National Research Council of Canada. Equivalents to other units. Time units: 1 international second is equal to 1/60th minute, 1/3600th hour, 1/86,400th day, 1/31,557,600th Julian year. Frequency units: 1, more generally, equals 1, where times equals 1, in seconds per meter or in kseconds. 1. History of definition. Early civilizations constructed divisions in the day, but none used the term second, and none was a precursor to the modern second. The Egyptians since 2000 BC subdivided daytime and nighttime into 12 hours each, hence the seasonal variation of the length of their hours. The Hellenistic astronomers Hipparchus and Ptolemy subdivided the day into 60 parts. They also used a mean hour, simple fractions of an hour, and time degrees. The Babylonians after 300 BC also subdivided the day using the sexagesimal system, and divided each subsequent subdivision by 60. That is, by 1/60th, by 1/60th of that, by 1/60th of that, etc., to at least 6 places after the sexagesimal point, a precision equivalent to better than 2 microseconds. The Babylonians did not use the hour, but did use a double hour lasting 120 modern minutes, a time degree lasting 4 modern minutes, and a barleycorn lasting 3 1/3 modern seconds, but did not sexagesimally subdivide these smaller units of time. No sexagesimal unit of the day was ever used as an independent unit of time. Based on subdivisions of the moon cycle in 1000, the Persian scholar al-Biruni, writing in Arabic, first used the term second, and defined the division of time between new moons of certain specific weeks as a number of days, hours, minutes, seconds, thirds, and fourths. Afternoon Sunday. In 1267, the medieval scientist Roger Bacon, writing in Latin, defined the division of time between full moons as a number of hours, minutes, seconds, thirds, and fourths. Afternoon on specified calendar dates. The modern second is subdivided using decimals, although the term third remains in some languages, for example Polish and Turkish. Based on mechanical clocks, the earliest clocks to display seconds appeared during the last half of the 16th century. The second became accurately measurable with the development of mechanical clocks keeping mean time, as opposed to the apparent time displayed by sundials. The earliest spring-driven timepiece with a second hand which marked seconds is an unsigned clock depicting Orpheus in the Fremersdorf collection, dated between 1560 and 1570. During the third quarter of the 16th century, Taqi al-Din built a clock with marks every 1/5 minute. In 1579, Jos Bergi built a clock for William of Hesse that marked seconds. In 1581, Tycho Brahe redesigned clocks that displayed minutes at his observatory so they also displayed seconds. However, they were not yet accurate enough for seconds. In 1587, Tycho complained that his 4 clocks disagreed by plus or minus 4 seconds. In 1644, Maron Massena calculated that a pendulum with a length of 39.1 inches would have a period at 1 standard gravity of precisely 2 seconds. 1 second for a swing forward and 1 second for the return swing, enabling such a pendulum to tick in precise seconds. In 1670, London clockmaker William Clement added this seconds pendulum to the original pendulum clock of Christian Huygens. From 1670 to 1680, Clement made many improvements to his clock and introduced the long case or grandfather clock to the public. This clock used an anchor escapement mechanism with a seconds pendulum to display seconds in a small subdial. This mechanism required less power, caused less friction and was accurate enough to measure seconds reliably as 1/60th of a minute than the older Verge escapement. Within a few years, most British precision clockmakers were producing long case clocks and other clockmakers soon followed. Thus the second could now be reliably measured. In 1832, Gauss proposed using the second as the base unit of time in his millimeter-milligram second system of units. The British Association for the Advancement of Science in 1862 stated that all men of science so agreed to use the second of mean solar time as the unit of time. Bars formally proposed the CGS system in 1874, although this system was gradually replaced over the next 70 years by MKS units. Both the CGS and MKS systems used the same second as their base unit of time. MKS was adopted internationally during the 1940s, defining the second as 1/86,400th of a mean solar day. Based on a fraction of a year in 1956, the second was redefined in terms of a year for a particular epoch because, by then, it had become recognized that the Earth's rotation on its own axis was not sufficiently uniform as a standard of time. The Earth's motion was described in Newcomb's tables of the Sun, which provided a formula for estimating the motion of the Sun relative to the epoch 1900 based on astronomical observations made between 1750 and 1892. The second was thus defined as the fraction 1/31,556, 925.9747 of the tropical year for 1900 January 0 at 12 hours ephemeris time. This definition was ratified by the 11th General Conference on Weights and Measures in 1960, which also established the international system of units. The tropical year in the 1960 definition was not measured but calculated from a formula describing a mean tropical year that decreased linearly over time, hence the curious reference to a specific instantaneous tropical year. This was in conformity with the ephemeris time scale adopted by the IAU in 1952. This definition brings the observed positions of the celestial bodies into accord with Newtonian dynamical theories of their motion. Specifically, those tables used for most of the 20th century were Newcomb's tables of the Sun and Brown's tables of the Moon. Thus, the 1960 SI definition abandoned any explicit relationship between the scientific second and the length of a day, as most people understand the term. Based on cesium microwave atomic clock. With the development of the atomic clock in the early 1960s, it was decided to use atomic time as the basis of the definition of the second, rather than the revolution of the Earth around the Sun. Following several years of work, Louis Essen from the National Physical Laboratory and William Markowitz from the United States Naval Observatory determined the relationship between the hyperfine transition frequency of the cesium atom and the ephemeris second, using a common view measurement method based on the received signals from radio station WWV. They determined the orbital motion of the Moon about the Earth, from which the apparent motion of the Sun could be inferred, in terms of time as measured by an atomic clock. They found that the second of ephemeris time had the duration of 9,192,631,770 plus or minus 20 cycles of the chosen cesium frequency. As a result, in 1967 the 13th General Conference on Weights and Measures defined the SI second of atomic time as the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. This SI second, referred to atomic time, was later verified to be in agreement, within 1 part in 1010. With the second of ephemeris time as determined from lunar observations. During the 1970s it was realized that gravitational time dilation caused the second produced by each atomic clock to differ depending on its altitude. A uniform second was produced by correcting the output of each atomic clock to mean sea level, lengthening the second by about 1 × 10⁻10. This correction was applied at the beginning of 1977 and formalized in 1980. In relativistic terms, the SI second is defined as the proper time on the rotating geoid. The definition of the second was later refined at the 1997 meeting of the BIPM to include the statement, "This definition refers to a cesium atom at rest at a temperature of 0 K." The revised definition seems to imply that the ideal atomic clock contains a single cesium atom at rest emitting a single frequency. In practice, however, the definition means that high-precision realizations of the second should compensate for the effects of the ambient temperature within which atomic clocks operate, and extrapolate accordingly to the value of the second at a temperature of absolute zero. Proposed. Based on optical atomic clock today, the atomic clock operating in the microwave region is challenged by atomic clocks operating in the optical region. To quote Ludlow al., in recent years, optical atomic clocks have become increasingly competitive in performance with their microwave counterparts. The overall accuracy of single-trapped ion-based optical standards closely approaches that of the state-of-the-art cesium fountain standards. Large ensembles of ultra-cold alkaline earth atoms have provided impressive clock stability for short averaging times, surpassing that of single ion-based systems. So far, interrogation of neutral atom-based optical standards has been carried out primarily in free space, unavoidably including atomic motional effects that typically limit the overall system accuracy. An alternative approach is to explore the ultra-narrow optical transitions of atoms held in an optical lattice. The atoms are tightly localized so that Doppler and photon recoil-related effects on the transition frequency are eliminated. The Canadian National Research Council attaches a relative uncertainty of 2.5 times 10⁻11 to their atomic clock based upon the 127I2 molecule, and is advocating use of an 88 senior ion trap instead. See magneto-optical trap and trapped ion optical frequency standards. National Physical Laboratory. Such uncertainties rival that of the NIST F1 cesium atomic clock in the microwave region, estimated as a few parts in 1016 average over a day. SI multiples. SI prefixes are commonly used to measure time less than a second, but rarely for multiples of a second. Instead, the non-SI units minutes, hours, days, Julian years, Julian centuries, and Julian millennia are used. Other current definitions. For specialized purposes, a second may be used as a unit of time in timescales where the precise length differs slightly from the SI definition. One such timescale is UT1, a form of universal time. McCarthy and Seidelman refrain from stating that the SI second is the legal standard for timekeeping throughout the world, saying only that, over the years UTC, which ticks SI seconds, has become either the basis for legal time of many countries, or accepted as the de facto basis for standard civil time.